a particle nature of the little particles. Now, we know little particles are particles, but when they are so tiny, they move at a different way compared to the regular microscopic, say, a baseball, and then they may exhibit what we call a wave nature. A wave is part of the electromagnetic radiation. Okay, so also based on the observation in the laboratory, with a particular type of element, when you give them some form of energy, say electricity, if you have hydrogen gas trapped inside a glass tube, and if you pass electricity through it, hydrogen gas, the atoms of hydrogen gas will actually absorb that energy. As a result, emit certain types of radiation. Now that certain type of radiation is not in a continuous spectrum, rather it's in single lines. In different colors in the visible region, in the invisible region you can also detect the radiation there. Each element has a different or unique emission line spectrum. Now, where does that come from, or why? And how can we use the emission line spectrum to identify different types of elements? So we're going to look at these different things there. And the first thing about the origin of the quantum mechanics there. In around 1900s there, scientists know that elements are made of atoms and electrons and nuclears and positively charged and negatively charged, and positively charged, and that's proton, and no charge, neutron. So we have nucleus, protons and electrons there, protons and neutrons there, and we have electrons. Okay, so in this case, now how are the electrons of an element? And that's the question we ask. If you have one, when we propose the structure, well, when Niels Bohr proposed the structure, so how does the electron how is the electron being distributed around the positively charged? How are the electrons of an element if you have more than one? We know now the theory, we know that they're circulating around the positively charged center. Now, if you have more than one, what's the relationship between the two electrons, or among more than two electrons there? So what we're trying to study, what we're trying to understand is that we want to study the electromagnetic radiation, because that radiation has something to do with the motion of electrons there, with the motion of very tiny particles there. So by studying how elements absorb and emit electromagnetic radiation, we can understand the behavior and the distribution of the electron around the atom there. So electromagnetic radiation, that's a large term. It's basically light. Okay? Light is composed of two vectors. They're perpendicular to one another, but they propagate toward the same direction here. So we have an electromagnetic, we have an electric wave, we have a magnetic wave. So in this case, we have the blue-colored vector and the pinkish-colored vector there. So we use the red-colored, pinkish-colored representing the magnetic vector there. We use the blue-color representing the electrical vector there. And they are perpendicular to one another at 90 degrees, 90-degree angle. And they are propagating towards the same direction. So when you talk about light, when you talk about electromagnetic radiation, there are always those two components in there. Okay? So wave would travel through space as vibrating electrical and magnetic field. And the fields are caused by the vibrating charge in the source. And where is the source? When you flip the switch, electricity goes through. The energy passes through, say, the gases that we put in the light bulbs there, and then those gases absorbing the energy, and they start to emit light. So the source is that switch there. When you supply the energy there, you see lighting, and you see electromagnetic radiation. Okay. Once again, this is an enlarged picture of the electromagnetic radiation. Well, what's in electromagnetic radiation? We have a magnetic vector, we have electrical vector. Always remember they are perpendicular to one another and they're propagating towards the same direction. Okay, so the speed of energy transmission is different depending on the form of the speed, the form of the energy there. So you hear the sound, and while sound is a mechanical wave and actually carries a certain amount of energy. So when you have very loud noise, and actually sometimes hurts, and because it also carries a certain amount of energy. When that energy hits you, Sometimes it could be enlightening, and sometimes it can be annoying. So it depends on whether it's music or noise there. But speed of the energy transmission, we know lightning is another type of speed. Lightning travels much faster. Electromagnetic radiation travels much faster. And this is the rate speed of light. 3.00 times 10 to the 8 meters per second. Okay. 10 to the 6 is a million, so that's 300 million meters per second. Okay. So that's a very fast speed. Compare that to the sound. The sound only travels at 340 meters per second. Okay. And every time you hear the term supersonic jets, and you think, it's traveling much faster, very fast. But light travels much faster. So different types of energy will propagate through space and actually travels at different speed. Now, for those wave functions there are properties associated with wave. And the first thing that we want to introduce is what we call the wavelength. Now, the wavelength, by definition, is actually the distance between two consecutive points. It doesn't have to be peaks or troughs. Any points there. So between these 2 points or these 2 points, that's a wavelength. Or between these 2 points, that's a wavelength. So any two successive points in a wave, the distance between those 2 points is how we define wavelength. Now, wavelength, we use a Greek letter, lambda, to represent wavelength. Wavelengths can be measured in meters, centimeters, nanometers. So you can see the wavelength for different vibration, for different waves there, and we can have very long wavelength, very short wavelength. Units range from nanometers, 10 to the -9th meter, to meters there. So that's a fairly large range there. Okay. And the other property of the wave is frequency. How fast are they traveling? Now, the number of complete wavelengths that passes a given point in space in 1 second is how we define frequency. And Hendrik Hertz, the Danish scientist who studied the properties of mechanical waves, and first, use the word discovered this property. Well, he did some intensive research about the frequency, the relationship between how fast the wave travels, and then what and the property of the waves there. So we use his name in honor of his research. And frequency, we use a Greek letter, nu, and the unit is 1/2 or we call it hertz. 1/2 is a hertz. Okay. So now that we have properties, two different properties of the waves there. We have wavelength, we have frequency. Now, for any wave, not just electromagnetic radiation, for any wave, speed equals to frequency times the wavelength. So for electromagnetic radiation, wavelength times frequency also give you the speed. Now we know speed of light is a constant number. So not 2.998, so more than often you see 3.00 times 10 to the 8 meter per second. You can use either number there. Okay? So the wavelength versus the frequency versus the speed of light. And when we plot the wavelength and the frequency there, this is what we got. So the wavelength is defined by two successive points in the wave, and the frequency is how many wavelengths does it pass a particular point in 1 second.